Okay, I hope I'm audible to all my students who are attending this online lecture for the Econometrics course. In this online lecture, I'm going to start with the first main module within the Econometrics course. This is the simple linear regression model. Okay, the book I prefer to follow for my lectures on this particular course, this is Introductory Econometrics by Wooldridge. This is one of the standard textbooks I follow for my lectures in econometrics. Now, since this is going to be an introduction to the simple linear regression model, students should have some idea about the basic math and probability, which we cover in our statistics course. Okay, so a refresher for the introductory econometrics course is the statistics, the concept of random variables. Students should be familiar with the concepts of probability, the concept of discrete and continuous random variables. You should know the concept of estimation and hypothesis testing. And students should also be familiar with basic differentiation and calculus. Okay, so let's quickly start with the discussion of simple linear regression model. Let's understand what is a linear regression model. What does it talk about? Okay, I'm going to make all students write detailed notes. If you follow these notes, you can keep your university lecture slides and the book aside. These notes are made from the standard textbook, which I follow, which is Introductory Econometrics by Wooldridge. Okay, and you can safely rely on the notes I'm making you write for your university level econometrics exam. During the course, I'm also going to solve a lot of back problems from the Wooldridge textbook, which is going to boost your confidence in preparing for your university exams. So let's quickly start with the discussion of introduction to simple linear regression in this online lecture. So I'm just writing the main heading for clarity. We are looking at simple linear regression model. Simple linear regression model. Formally, this is chapter 2 of the book I'm following as reference. This is chapter 2 of the book Introductory Econometrics by Jeffrey Wooldridge. Introductory Econometrics by Jeffrey Wooldridge. Okay, so let's quickly understand what will a simple linear regression model capture. So we take into consideration two variables. One is called y, one is called x. So I can write that the simple linear regression model, the simple linear regression model studies how the random variable y varies with changes in another variable x. We call x as the independent or the explanatory variable. And as x changes, we will observe changes in y, which we call as the dependent variable or the response variable. So I can write a simple equation, okay, relating y to x. Looks like this. Y is a linear regression model, somewhat looks like this: beta naught plus beta 1x plus u. Okay, so we want to explain y in terms of x. I can write a note that the variable y, this is the first point within the note, the variable y is called the dependent variable. The variable y is called the dependent variable or the response variable. we are going to check the response of y to the variable x. Okay? And the variable x is called the regressor or the explanatory variable. It's called the regressor or the explanatory variable. Now, students must be wondering, what is beta naught, what is beta 1, and what is this variable u? So in math, when we write a linear function, remember we have something called the intercept term. So beta naught here denotes the intercept term. So I can write it like this. Beta naught is the intercept term. It gives us the value of y when x takes the value 0. Beta 1 is called the slope coefficient. If I differentiate y with respect to x, I get beta 1. So beta naught and beta 1 are the population parameters, and this whole equation is called the population regression function. The population regression function is going to explain how y varies with the random variable x in the population. So it's a population regression function. Short form, I can write PRF. How the random variable y changes with changes in the variable x in the population. Okay, so I can further add that beta naught is called the intercept parameter. Beta naught is the intercept parameter. And beta 1 is the slope parameter. Beta 1 is the slope parameter. Okay, now what does u capture? U captures nothing but the disturbance term. It's going to capture all other factors other than x which have an impact on y. All factors other than x. So I can write that the variable u is called the error term or the disturbance term. Is called the error term or the disturbance term. Okay, so why is it called an error term or a disturbance term? Because it is going to collect all those factors other than x which have an impact on y. It consists of all the factors other than x that influence y, or I can write that affect y. For example, when we talk about a simple demand function in microeconomics, we know that quantity demanded is influenced or affected by price. But quantity demanded of a commodity also depends upon a whole lot of other factors like tastes and preferences of the consumer, income of the consumer. It also depends upon the price of substitute goods and complement goods. So think of a simple demand function where U includes all factors other than price which have an impact on demand. Like income, tastes and preferences, price of substitutes and complements, number of buyers, price expectations, and so on. So if I sum up, so far, we have started our discussion of the simple linear regression model. We are going to learn how y is going to vary with x. So when x changes, what's the impact of that on y? So y is called the dependent or the response variable. X is called the explanatory variable or the regressor. Beta naught is the intercept term. Beta 1 is the slope parameter. Okay, this whole equation which students can see, beta naught plus beta 1x plus u, is called the population regression function because it's explaining how y varies with x in the population. U is the disturbance term which is going to capture all factors other than X that can have a possible impact on Y. Okay, now let's do a bit of algebra. Suppose I want to look at now change in this regression equation. So let's say if I go back to the original regression equation, this is y equals beta naught plus beta 1x plus u. Now let's dig deeper into the slope. How do we calculate that? So how will I calculate the change in values? Let's say this is y1 equals beta naught plus beta 1 x1 plus u. Let's say this is equation number 1. This is u1. Similarly, this is my initial equation. And suppose my another equation is y2 equals beta naught plus beta 1 x2 plus u2. Let's say I have two regression equations for two different values, y1 x1 and y2 x2. Remember, beta naught and beta 1 are parameters, they are not changing. Okay, now how do I calculate the change? How do I calculate the change? The change is nothing but the new minus the initial, right? So I can write y1, y2 minus y1 is equal to this whole equation beta naught plus beta 1 x2 plus u2 minus beta naught plus beta 1 x1 plus u1. Remember, these are not powers, these are merely values. Now y2 minus y1 I can call change in y is equal to beta naught plus beta 1 x2 plus u2 minus beta naught minus beta 1 x1 minus u1. I just opened up the brackets. Beta naught minus beta naught cancels out. I can just take the beta 1 terms together. So beta 1 times x2 minus x1 plus u2 minus u1. So this I can write as delta y is equal to beta 1 times delta x plus delta u. Okay. Now, when will delta y be equal to beta 1 delta x? When delta u is equal to 0. So I can write that delta y is simply beta 1 delta x when delta u, or when the change in the error term, is equal to 0. So I can, students, now I can write, if I take change in x in the denominator, change in y over change in x is equal to beta 1. So what does beta 1 measure? It measures the rate of change in y, per unit change in x, rate of change in y per unit change in x, holding all other factors fixed. When I write all other factors fixed, it means that is delta u is equal to 0. The moment I say that delta u is 0, it means that all other factors are constant, ceteris paribus. Because remember, I said that u captures what? U captures all other factors other than x, which can have an impact on y. So when I say that change in u is 0, it means all of the factors are constant. So what do we learn? Beta 1, which is the slope parameter, is going to capture the rate of change in y per unit change in x when all other factors are constant. That means when delta u is 0. Okay, so I can write that, in other words, the simple linear regression captures a ceteris paribus relationship. It captures a ceteris paribus relationship of x on y. So I'm quickly revising this portion again. Okay, we were trying to do what? We were trying to, after all, interpret beta 1. Beta naught is the intercept term. Okay, beta naught simply tells us the value of y when x takes the value 0. Okay, so what we were trying to do and what we are mainly interested in doing is to interpret the beta 1 parameter. Now, how do we interpret the beta 1 parameter? We look at the change in the regression. How do I capture the change? Change is always the new values minus initial values. Let's say the initial values were y1 and x1 and u1, and the new values were y2, x2, and u2. Beta naught and beta 1 are the same because they are population parameters. They are not changing. How do I capture the change? The new equation minus the old equation. So y2 minus y1 is equal to this whole equation minus this whole equation. This is how we find the change. If I work it out, I get change in y is equal to beta 1 change in x plus change in u. And if change in u is 0, change in y is beta 1 change in x, which I can write as change in y over change in x is equal to beta 1. That means beta 1, which is the slope coefficient of the regression, will capture the rate of change in y for a per unit change in x, keeping all other factors constant. When I say all other factors constant, it means that my error term is not changing. Delta u is 0. Okay, so I hope so far students are clear. Now, in econometrics, what we are interested in estimating is these population parameters beta naught and beta 1. As an econometrician, we are interested in looking at estimates of beta naught and beta 1 because population is very large. We don't know the population. I can only estimate the population parameters for which I will be conducting a sample. I will be taking a random sample. Okay, so I can write that when it comes to estimating using a random sample, okay, we are going to take a random sample and we are going to see how ceteris paribus, how x impacts y in the sample. Okay, so hoping students are clear with this and have no doubts. So if I now move forward, we are going to make a very interesting assumption now. This assumption is going to talk about the relationship between u and x. Okay, so I can make all students write further a note before I jump to that crucial assumption. When it comes to estimating, beta naught and beta 1, which are my population intercept term and slope coefficient respectively, using a random sample of data, and thus estimating the ceteris paribus effect, of x on y, we must restrict how u and x are related to each other. So what I'm trying to convey to all students is that when I'm now doing sampling, my objective is to estimate beta naught and beta 1. I have to make sure as to what is the relationship between u and x, because I just said that u includes all factors other than x, which can have an impact on y. So when I'm now doing sampling, I need to be clear about the relationship between u and x. Are they related at the first place or are they not related? To understand this, students, the first key assumption we make, students can write this. The first key assumption we are going to make is that expected value of u will be 0. That means now expectation of a random variable is a concept which I have covered up in my statistics course. Remember, I said in the beginning of the lecture that the statistics course is a refresher for this econometrics course. So I can write where E denotes the expected value. So what we are trying to say is that On an average, the error term takes the value 0. It means when I'm doing sampling, the error term sometimes will take positive value, sometimes it will take negative values, but on an average, the positive and the negative values sort of cancel out each other, causing the expected value to be equal to 0. Okay, so I hope students are clear with this. What does this mean? This means that on an average, the error term in the population takes the value 0. The error term in the population takes the value 0. This is what I'm trying to say. Okay, so let's say it is not 0. So what is going to happen in that case? So I can say that suppose expected value of u is, let's say, not equal to 0. Say expected value of u is equal to some value alpha naught. Then how will my regression change? I can write that y is going to be beta naught plus beta 1 x plus u. This was my original population regression function. I can add and subtract alpha naught in this regression. So I can write it like this: beta naught plus alpha naught plus beta 1 x plus u minus alpha naught. What did I do, students? I added and subtracted alpha naught. Maths allows me to do that. Added and subtracted alpha naught. I added here and then I subtracted it here. Now I can call beta naught plus alpha naught as my new intercept term beta naught star, plus the slope coefficient remains the same, beta 1x, and I can call u minus alpha naught as u star. So what is my new error term now? My new error term, the new error term is u star, which is simply u minus alpha naught. And you can see that this new error term satisfies the assumption that expected value is 0. Now consider expected value of u star. Let me show it to all students. Expected value of u star will simply be expected value of u minus alpha naught, which I can write using properties of expectations as expected value of u minus expected value of alpha naught. Expected value of u itself is equal to alpha naught, and expected value of alpha naught is alpha naught only, because expectation of a constant is the constant itself. Now alpha naught minus alpha naught is 0. So students, what did I learn? The moment I transform the regression, my new error term on an average takes 0 value. What is not changing? In this whole process, beta 1 did not change. The moment I violated the assumption, the moment I said that expected value of u is not equal to 0, I just simply got a new intercept term. From beta naught, I got beta naught star. And from u, I got u star. But then u star satisfied the assumption expected value of u star is equal to 0. So I can write this. I can write that the new intercept term is beta naught star equal to beta naught plus alpha naught. You can see in the regression that beta naught plus alpha naught is equal to beta naught star, and the slope beta 1 does not change. The slope beta 1 does not change. So what do we learn? We learn that if the average of u is different from 0, that is, if the expected value of u is not equal to 0, we just adjust the intercept term. which is what we did. From beta naught, we went on to beta naught star, the new intercept term. We just adjust the intercept term and the slope remains the same. The slope, which is beta1, remains the same, as students can clearly see. Okay, so this whole analysis was done to indicate to all students that expected value of u should be equal to 0. This is one of the key assumptions regarding the population regression function. The expected value of the error term should be 0. If it is not 0, our intercept term will change from beta naught to beta naught star, and the error term will change from u to u star, such that the new error term u star on an average will take the value 0. So another thing we learn is that expected value of u not equal to 0 does not change the slope. The moment I said that expected value of u is not equal to 0, the slope did not change. It was beta 1. Here also it's beta 1. What changed? The moment I made this assumption of expected value of u not equal to 0, what changed is beta naught changed to beta naught star. U changed to u star. Nothing happened to beta 1. Okay. The second key assumption. So this was the first key assumption. So students can write here for clarity. This is key assumption 1. Now we are looking at the second key assumption we are going to make. So key assumption 2. Key assumption 2 is coming from key assumption 1 only. The key assumption 2 we are making is that the expected value of u conditional on x is exactly equal to expected value of u. That means u does not depend upon x. So I can write that the second key assumption, is on the expected value of u. The second key assumption is on the expected value of u given x. Or I can write, in other words, the mean of the error term, for the population determined by the values of x. For the population determined by the values of x. So students, what I'm trying to say is that expected value of u conditional on x is exactly equal to expected value of u for all values of x. It means x has no impact on u. X has no impact on u. So this means what? This means that u, which is my error term, is mean independent of x. Whether x occurs or does not occur, it does not impact u. For example, to understand this, let's take an example. The example I'm trying to take here is, let's say, suppose my error term u denotes the ability of a student. And let's say, hypothetically, x denotes the years of education. Or I can say, yeah, let's take x as years of education. Let me be consistent with the book only. Okay. So if I follow this assumption, given the above assumption, what I'm trying to say is that expected value of ability for a student in, let's say, 8th standard is equal to expected value of ability for a student in 12th standard is exactly 0. It means your ability is not affected by which standard you are in. Although students might be thinking that this is a bit unrealistic because you would expect a 12th grade student to have more ability. But I have just taken an example to explain it to all students. You can think of, if you think that years of education is not a very suitable example, you can think of X as something to do with, let's say, your height. So your height is not impacting your ability. People with lower height can also be able to do tasks. So the second key assumption is telling us what? It's telling us that expected value of u is not influenced by x. It means expected value of u conditional on x is equal to expected value of u only. That means u has nothing to do with x. When x changes values from 8 to 12, the expected value of ability is not changing. It is still the same. Okay, and now comes the next part. It is equal to 0. This is what the next part I'm trying to explain also. That means we just said that expected value of u is 0, right? From the first assumption. From the first assumption, we just said that expected value of u is 0, right? If expected value of u is 0, it means expected value of u conditional on x is also 0. Because the second key assumption is that expected value of u conditional on x is equal to expected value of u. So what do we learn? We learn that if I combine assumptions 1 and 2, combining assumptions 1 and 2, we learn that expected value of u conditional on x is equal to expected value of u equal to 0. This is called the zero conditional mean assumption. This is called the zero conditional mean assumption. What does it state? I can write, it says that the expected value of the error term, the expected value of the error term is 0 regardless of the value of the explanatory variable x. Regardless of the value of the explanatory variable x. So I hope students are understanding this. This assumption, the first assumption was telling us that u is, the first assumption was telling us that expected value of u is 0. That means in the population, on an average, u takes the value 0. The second assumption was telling us that u is mean independent of x. It means that occurrence of x has no impact on expected value of u. Expected value of u conditional on x. The moment, remember, if we did conditional probability, it means expected value of u when x has occurred is exactly equal to expected value of u. It means u and x are independent. X is not having any impact on u. If I combine these assumptions, what we learn is that expected value of u conditional on x is simply 0. That is why it's called zero conditional mean. Why is it conditional? Because it's conditional on the x. It means in the population, the error term u on an average takes the value 0 for a given value of x. Okay, so now given that I have y equal to beta naught plus beta 1x plus u, if I take expectation on both sides, taking conditional expectation on both sides, taking conditional expectation with respect to x, taking conditional expectation with respect to x on both sides, I can write, we get expected value of y conditional on x as expected value of beta naught plus beta 1 x plus u conditional on x. What is y? Y is this only, right? Beta naught plus beta 1 x plus u, my population regression function conditional on x. This I can write as expected value of beta naught plus expected value of beta 1 x plus expected value of u conditional on x. Remember guys, beta naught is a constant, it's a population parameter. Expected value of a constant is the constant itself. Similarly, expected value of beta 1x is also beta 1x, because beta 1 is a constant and x also has no probability distribution attached to it. X is not a random variable, remember. Y is a random variable. X doesn't take different values with different probabilities. X takes fixed values. Because X takes fixed values, expected value of X is X itself. And we just said that expected value of U conditional on X is 0. We just said that expected value of U conditional on X is 0. That means I can write therefore expected value of Y conditional on X is just beta naught plus beta 1x. This is called the population regression function as a linear function of x. This gives us the population regression function. This gives us the population regression function. Expected value of y conditional on x as a linear function of x. Let me write this clearly as a linear function of x. Linear function of x. Okay, so it's going to tell us how x has an impact on the expected value of y or the average value of y. Okay, so I stop in this particular lecture. This was an introductory lecture. Okay, we have started our discussion from chapter 2 of Wooldridge. Okay, it's all to do with understanding the simple linear regression model. We have primarily made two assumptions. First assumption is that on an average, the error term takes the value 0 in the population. The second assumption we have made is that the conditional mean of the error term is 0. That means expected value of u conditional on x is 0. Okay, we have also learned that x has no impact on u in the population. And using this, we have derived the population regression function as a linear function of x. So in the next lecture, I am going to move forward with the same topic, and I'm going to look at the concept of ordinary least square estimates. Now I'm going to dig deeper into the sample. In this lecture, we are talking about the population. Now we are going to go into the sample. So ordinary least square estimates. We are going to derive them in the next lecture. So I stop in this lecture. I hope students have enjoyed this lecture. Any doubts, you can unmute your mics and ask, or you can get in touch with me for doubts on call or WhatsApp, or you can mail me your doubts at divineschoolofeconomics@gmail.com. This is where I stop in this lecture.